Yes, so this session is about the finite state machine. We are going to discuss about what do you mean by finite state machine, how you are going to develop your Verilog coding with respect to your finite state machine, and we are going to discuss some more interesting and new things in finite state machine. Hope someone knows them, and if you are not aware of them, let us try to understand them. Okay, yeah. So let us start with the basic full form of FSM. It is nothing but finite state machine, right? I think most of you know about what do you mean by FSM and categories of FSM, right? So what are the two different categories do we have in FSM? Anyone wants to answer this? What are the two different categories of finite state machines do we have in our yeah, Mealy and Moray, exactly. So we have Mealy FSM and Moray FSM, right? So FSMs are basically classified into two types. One is Mealy FSM and another is Moray FSM, right? So this FSM is classified into two types. One is Mealy and another is Moray. Okay, that's great. Can you tell me what do you mean by Mealy and what do you mean by Moray? What do you mean by Mealy and what do you mean by Moray? What do you understand by Mealy FSM and what do you understand by Moore FSM? Mealy has both input and output. Okay. Moore don't have a. No one knows the difference between Mealy and Moore FSM. Mealy is asynchronous and Moore is synchronous. Moore depends upon the previous state. Mealy depends upon input and previous state. Okay. So you're saying correct only, but you're missing one particular point is output. Here, in the case of your Mealy, output is dependent upon input as well as present state. Whereas in the case of my Moore, output is only dependent upon my present state. Okay. And here, since output is dependent upon input and present state, this can be said as asynchronous. And here, uh, since your output is only dependent upon the present state, it is known as it is synchronous in nature. Moore is synchronous in nature, whereas your Mealy is asynchronous in nature. Okay. Yeah, Moore is dependent upon current state. Okay, exactly. So here my question over here is we have two terminologies. So when you're learning anything, so if you find any new term like present state, right? So we have some terminology like present state. So what do you understand by present state? And in FSM, if you have worked with Verilog coding, you have also heard about this terminology next state. So what are these terminologies? Anyone wants to answer? What are these terminologies present state and next state? In many Verilog codings, you have might seen this if you have worked with like present state, next state. What do you mean by this present state and next state? Are they simple variables? PS and NS? Just some names? Okay. No answers? So what do you understand by present state and what do you mean by next state? Next state decides when the FSM moves to the next state. Okay. Okay. Present state put input value and previous state. Present state means initial state and next state means present state if one goes to next state. Okay. Okay. So first of all, let us try to clarify this present state and next state. What do I mean by this present state and next state? Because in coding, in Verilog coding, you will see them a lot. We don't know what are they exactly, but we use them a lot. Okay. So let us try to understand. So let's say if we take a one bit D flip flop. Okay. If we consider a one bit D flip flop, then how many flip flops we are going to have for one bit D flip flop? Is the question. For one bit D flip flop, how many states? Sorry, how many FSM? Sorry, how many flip flops do we have? Yeah, one D flip flop, right? So I'm going to have one D flip flop. So this is D, this is Q, and this is Q bar. Okay. Now this is my output. Let's say this is my output over here, and this is my clock. Okay. And here I'm going to provide my input. Okay. This is obvious, very easy circuit diagram we have with us. Now, at present, if my at present at the first clock edge, what is the output of this flip flop? If my input is equal to 0 previously before this clock edge, like let's say somewhere here, my input was equal to 0. Now, at this present clock edge, at the first clock edge, what will be my output? Anyone wants to answer? It's simple, 0, right? Yeah, exactly. So here my output is equal to 0. And at this particular first clock edge, I'm going to provide input is equal to 1. So what will be my next output? What will be my next output? So obviously, next output will be present at the next clock edge, right? So if you're going to provide the input over here, you will get your output at the next clock edge. Am I right or wrong? Yes or no? Am I drawing it correctly? Will I get will I get my output exactly when I'm going to provide my input? No, right? I will get my output at the next clock edge. Am I right or wrong? Yes, obviously, right? Now, what will be your output at the next clock edge? It will be equal to 1. Output will be equal to 1. And let's say at the second clock edge, if you are going, so this is so if we came to the second clock edge, this will be our present output, and this is nothing but my past output. Okay, here reference is very important. If we are in the second clock edge, present output is 1, past output is 0, and depending upon the present input, we are going to decide the next output. Am I right or wrong? Depending upon the present input, we are going to decide my next output. Here, the next output will be equal to uh, 0. Okay. Yeah. Yes. Uh, what exactly you want? Okay. Okay. So let's take 2 bit. Okay. So for 2 bit, this is how my 2D flip flops are going to look like. Okay. So this is, let's say this is D1, Q1, D0, and Q0. And these are my clocks, which I'm going to have. Okay. And let's say this is my input, which I'm going to have, and direct connection with this. And this is my Q0. Okay. And this is my Q1, which I'm going to have. Okay. Now, this is my clock, which I'm going to have. Okay. This is my clock edges, which I'm going to have. Now, so this is the first clock edge, which I am in. Okay. So this is where present I am in. Present I am in first clock edge. And previously, the input present to this D1 is equal to 0. And here also Q1 is equal to 0, right? So D0 is also equal to 0. Now, at the first clock edge, what is the value of Q1 and what is the value of Q0? Anyone wants to answer? What will be the values of Q1 and Q0 if previously input was equal to 1? Obviously, it will be equal to Q1 will be equal to, sorry, if input was equal to 0, Q1 is equal to 0 and Q0 is equal to 0, right? Now, at this passage of clock, if you are going to provide input is equal to 1. Now, what will be my next clock values? What will be my Q1 and what will be my Q0? Q1 will be equal to 1. And what about Q0? 0, right? So depending upon your present input value, you are calculating your next state values, next output values. Am I right? So at present, if you are providing any inputs, then next you are going to get your outputs. At the next cycle, you are going to get your outputs. Am I right or wrong? Yes or no? Yeah. So Here, this is nothing but my present state and next state. If you carefully observe, at this particular point of time, what is your output? Q1 is equal to 0, Q0 is equal to 0. Or at this point of time, if your input is equal to 1, what is your output? This is nothing but your present state. Present state is nothing but what is your output of the flip-flop. That is known as your present state. Okay. So here present state is nothing but output of the flip-flop at present cycle, here at this first cycle, and here q1 and q0 values at this first cycle. Okay, now what do you mean by next state? Next state is at the next cycle, what is the output of your flip-flops, and who is going to decide your next state here, guys? Who is basically deciding your next state? Next state is nothing but at the next cycle output of the flip-flop, but who is deciding that next state? Input is deciding, exactly. So basically, input is basically deciding your next output in this particular circuit I'm talking about, right? So in this particular circuit, here also, my basically output is basically dependent upon my input. So next state is nothing but output of flip-flop at next cycle, and it depends upon my input. So these are the terminologies which we often use, but we don't know the exact meaning of what do you mean by present state and next state. I hope now they are clear, right? So what do you mean by present state and what do you mean by next state? Okay. I hope these are clear, right? Okay. Yeah. So why we are discussing them? Because we need these terminologies. We use them a lot, but we don't know exactly what is their meaning. So yeah. Now, coming back to my Mealy FSM and More FSM, here output is dependent upon input as well as present state. Present state is nothing but exact output of your flip-flop. And here output is only dependent upon exact output of your flip-flop. Okay. So that is nothing but my present state. Nowhere next state is next state we don't want for determining my output. Okay. Now, so let's try to understand your Mealy. Okay. So in the case of your Mealy FSM, as we have discussed previously, that your output is dependent upon your present state as well as input. This is what we have discussed, right? So your output is basically dependent upon your present state as well as input. Now, so if I want to draw the FSM state diagram, so how it is going to look like? So I'm going to have some states. So this is, let's say this is S1 and this is S2. So S1 is nothing but this is a representation of your present state. This is nothing but your present state. That means, let's say, suppose in this particular circuit, presently at the first cycle, what is my Q1 and what is my Q0? It is 0, 0 now. So Q1 is equal to 0, Q0 is equal to 0 whenever your clock, whenever we have the first clock edge. So we are representing this particular Q1 is equal to 0 and Q0 is equal to 0, the outputs of this flip-flop, as some diagrammatical representation as S0. Now, let's say if this flip-flop has changed its state, and in the next state we are getting Q1 is equal to 1, Q0 is equal to 0. So instead of writing output of first flip-flop is 1 and output of second flip-flop is 0, we are representing this in diagrammatical representation as S1 state. That's it. So if you find S1, then that means it is a some output of the flip-flop. And if you find S2, then it is nothing but it's a present state of your flip-flop. Okay. And how you are going from S1 state to S2 state, from this particular present state to this particular next state, who and how we are deciding? Anyone wants to answer? Exactly. So based on the input, we are basically deciding from S1 state, are we going to S2 state, or else based on the input, are we staying in the same state? And since it's a Mealy FSM, our output is also dependent upon the input. So this is the FSM state diagram, how it is going to look like. Is it clear, guys? Yes or no? Yeah. Now, let's say if I want to design a FSM, so if I want to design a Mealy FSM for detecting, generally this Mealy FSM you might have seen for sequence detectors. So these are mostly and mainly asked. So let us try to have this discussion. Let's say if I want to design a Mealy FSM sequence detector for the sequence 0, 1, 1. What do I mean by this? Let's say if I have a block diagram like this. Okay. And this have inputs as clock, reset, and serial input, and my output. Here my output will become 1 whenever this particular black box detects the input 0, 1, 1. For example, if you're going to provide the serial input for every positive edge of the clock like this, so if you're going to provide your serial inputs like this, let's say suppose if you're going to provide 0, your output will be still 0 only. And if you're going to provide next 1, then output will be still 0 only. And next, if you're going to provide another 1, your output will should become 1. This is how your black box is going to work. If you're going to have the sequence 0, 1, 1 as your input, then your output will become 1, 0, 0. Your output will become 1 whenever you have provided your input is equal to 1. Okay. So this we need to design using our FSM. Let us see how to design it using our Mealy FSM. Now let's say if I have to design this, let's say if I'm going to apply the reset, I'm going to a state which is known as S naught. Now, what do I mean by this S naught is? S naught is a state which is nothing but output of the flip flop. It can be anything. Okay. So here S naught is a state where no bits are matching at all. Okay. So that's why in reset we are going to a state which is known as no bits are matching. If we are going to apply reset. Now from S naught, let's say we have two combinations. Our input can be equal to our in. We are going to evaluate the bits from the MSB. Okay. So let's say if my input can be equal to 0 or else my input can be equal to 1. Okay. Let's say if my input is equal to 0, where should I go? And if my input is okay, first let's say if my input is equal to 0, which state should I go? So S1 is a state where one bit is matching. Anyone wants to answer? If my input is equal to 0, which state should I go? S1 state. Exactly. S1 state. Now, why you are going to S1 state? Let's try to understand. You have the sequence 0, 1, 1. Okay. First, you need to get this 0 bit. Okay. So, you are providing from your input, you are providing the bit 0. That is what we want, right? So, that's why 1 bit is matching. So, that's why we are going to S1. Okay. Now, instead of providing 0 as my first bit, what I'm going to do is I'm going to provide 1 as my first bit. I'm going to provide 1 as my first bit. So what I want first is 0, but what I'm providing first is 1. So is this requirement is getting matched, or is our requirement getting fulfilled? Obviously, no. Our requirement is not matching and no bits are getting matched. That's the reason I'm staying in the same state. Now, many gets confusion over here. Sir, one is matching with this now, one is matching with this now. You might say one bit is matching now. No, first I need 0. Okay, this is the first input and I'm getting 1 as my first bit. I need to get first bit as 0, but I'm getting first bit as 1. That's the reason I'm going to stay in the same state. Okay, this is what matching means. Matching is not like you're matching with this one or you're matching with this one. No, your first bit should be 1. Sorry, your first bit should be 0. That is nothing but my 1 bit matching. Okay, so that's the reason if you're going to get 0, you're going to S1, and if you're going to get 1, you're going to stay in the same state. And here your outputs will be equal to 0. Okay, now if we are in S1 state, again, we have two options. One input can be 0 and another input can be equal to 1. Now tell me, where should I go if I'm going to get 1 over here? Yeah, why we are going? Okay, let's say first bit, yeah. First bit we have given 0. So this is matching. Now, what we are expecting? We are expecting 1 and we have given 1. So two bits are matching now. Okay, 0 is matching and 1 is matching, and our sequence is about to build. That's why what I'm going to do, I'm going to a state which is known as S2. Okay, now instead of this 1, what I'm trying to do is, So instead of this one, what I'm trying to do is I'm going to provide 0. Now what is going to happen? If I'm going to provide 0. So second bit I need to give 1, but I'm going to give 0 only. Now what is going to happen? Okay, why we need to go to S0? Because you can see the sequence is first we need to give 0, next we need to give 1. But first we are giving 0, okay. But next instead of giving 1, we are going to give 0. So nowhere there is a chance to build this sequence again. Okay. So that's why no bits are matching, right? That's the reason you're going to simply S0. Like this you're going. Yeah, S not state you're going. Is it clear how you are detecting it? Yeah. Now you are in S2 state. Okay, you have given 1 and you have successfully came to S2 state. Let me draw it. So I have successfully given 1 so that I have came into S2 state. Now in the S2 state I need 1 and I have two combinations again. So one input may be 0 and another input may be equal to 1. So let's talk about this 0 first. So let's say instead of giving 1, if I'm going to give 0, can you see anywhere the sequence is getting formed? No. Okay. So nowhere the sequence is getting formed, but you can see the starting sequence, the starting digit of this 0 1 1 is 0, right? So if I'm going to get 0, can I go to S1 state? Can I go to S1 state? Yes or no? Yes, I can go because you can see over here 0 1 0, your sequence is not getting matched, but using the 0, I can build this sequence, right? So at least one bit is matching now. That's why I'm going to S1 state. Is it clear? Everyone, is it clear? Yes, yes, I'm coming to that particular point only. So here, yeah, I'm coming to that particular point only. Here also in the S1 state, let me erase this. Here also in the S1 state, let's say if I have 0, okay. So you can see we have 1 0 and instead of 1, what we are expecting, we are getting one more 0. Since the sequence is not getting matched, you can simply go to S 0. There is no problem. But if you carefully observe, this 0 can be used as a starting bit of the sequence. Am I right or wrong? So that means one bit is matching. So I can stay in the same state only, right? If my input is equal to 0, I can stay in the same state only, right? Yes or no? Is it clear? Yes. Okay. So yeah. So I'm going to write down 1 and I've drawn here 1. Now, so instead of 0 over here, let's say if I'm going to get 1, then that means you can see 0 1 1 and 0 1 1. Sequence has matched or not? Yes or no? Yes. So the sequence has been matched and simply I'm going to S not state. Okay. And there will be something like overlapping and non-overlapping. I will discuss it later, but I want to discuss apart from that other thing which I want to discuss. So let's have the discussion about that. Okay. So this FSM, is it clear how to draw this FSM? Is it clear? Any doubts or any queries? Yes. Okay. Now, how to write the Verilog coding for this particular part? Anyone knows how to write the Verilog code for this? So if I want to write down a Verilog, sorry, yeah, yeah, please. I've not got your point. Can you repeat it again? Yeah, this is output, right? This is input. Yeah. If Yeah. So the condition over here is if your present state, if you are in S2 state, and if your input is equal to 1, then only you need to make your output as 1. But if you are in S2 state and if your input is equal to 0, your output is 0 only now. Your answer is in your question only. No, no. In If we are in S1 and if our input is 1, then only we are going to S2, not output. Because that is the condition now. You have sequence is not detected now. Your sequence is detected, then only you're going to make your output 1, right? 0, 1, 1. Here I have shown you, right? Where is this? Yeah, 0, 1, 1. Okay, okay, yeah. Now, coming to this Verilog code. So, those have already learned about when got final sequence and all. Yeah, yeah, exactly. Yeah. Now, so those who have already done this Verilog coding, can anyone answer like how to perform your Verilog coding for 0, 1, 1? What is the steps you are going to perform? Sorry? Okay, okay, okay. Yeah, someone has also, yeah, thank you for that. And someone has also answered this. Yeah. So basically, we will declare the module inputs and outputs, and we are going to declare some parameters, right? So we are going to declare the parameters, and S naught will be encoded as a two tick binary 0, 0, and S1 will be encoded as a two tick binary 0, 1, and S2 is encoded as two tick binary 1, 0. Here, what type of encoding I'm using? Here, this is binary encoding scheme. For S0 state, I'm going to give the values as 0, 0, and S1 I'm going to give 0, 1, and S2 I'm going to give 1, 0. Please remember this term. I'm using here binary encoding. Okay, I'm going to discuss this encoding scheme also for this FSMs, right? So in this particular example, I'm using a binary encoding. For the states, these are for 0, 0, I'm going to declare a parameter as S0, and for the next state, I'm going to declare the parameter as S1, and for 1, 0, I'm going to declare S2. Now, you might have also seen in Verilog coding in our videos only. Like if you have followed the Verilog playlist, I have shown you like how to develop your code. So we are going to have something known as present state logic. This is used to determine your present state. And next we are going to have next state logic. This is basically used to determine your next state. And if possible, you can have another logic as your output logic. Okay. If you don't know about this particular things, you can watch our playlist where we have discussed about FSMs also. At the end, it will be there in a Verilog playlist. Okay. So we have discussed that we are going to have present state logic, next state logic, and output logic. Okay. Now, yeah, yeah, I'm coming to that particular point. Okay. Present state. Yeah. The next question is that only. So, what is the present state logic? Is it sequential or is it combinational? So, generally, present state logic will be sequential, and next state logic will be combinational, and output logic will be combinational itself. And if you want to have the synchronization, you can make it as sequential. Okay. We'll come back to output logic, but how to remember present state logic? Because many times you will get confusion like present state logic, is it sequential logic or is it combinational logic? So just go back to the basic which we have started with. So what do you mean by present state? Present state is nothing but output of my flip flop. Present state is nothing but my output of flip flop. Now, output of flip-flop, is it sequential or is it combinational? Exactly, right? So present state is nothing but it's an output of flip-flop I'm saying, then obviously it's sequential, right? Okay. And how you're going to determine your next state, that we are going to see with some state transition table and all. We will first draw one circuit, and from that circuit I will get the conclusions about this next state, why it is combinational. Okay. Now, let's say if I'm going to have my state transition table like this, so I'm going to have my, first of all, let me encode them. So let's say S naught is binary encoded as Q1, Q naught. So I'm going to have 2 bits per encoding them. So let's say these are Q1, Q naught, and S1 is nothing but 0, 1, and S2 is nothing but 1, 0. Okay. These are the three states. And let's take S3 also, which is nothing but 1 and 1. Okay. Now, we don't have S3, but we are going to take. Okay. Now, let's say if I'm going to have my present state, let me write down my present state first. Next, I'm going to write down my next state. Next, I have input, and let me write down my input, because in equations, I'm going to take a present state input and next state, and this is my output. And let's take what flip flop? Let's take simply D flip flop. Let's take. Okay. So let's say this is D flip flop. Okay. So if I'm going to take a D flip flop, this is how it is going to look like. This is my Q1, Q naught, output of my D flip flops. And let's say my input is some M. Okay. And my next state will be Q1 plus and Q naught plus. Okay. And this is my output, let's say Y. Okay. Sorry for that. And coming to my D, I'm going to take two inputs, D1 and D0. I'm going to consider. So this is my output, and this is D1 and D0. Okay. It's nothing but it will look like your excitation table, right? So if we are in S0 state, that is 0, 0, 0, 0. This is my S0 state, S0 state. Okay. And input combinations have two combinations, 0 and 1. Okay. And if I'm in S1 state, I have again two combinations, 0 and 1. This is my S1 state arrow. Okay. And if I'm in S2 state, this is my S2 state, I'm going to be 0 and 1. Generally, we neglect this table. We don't look into this table because it's not necessary, we feel, but this is very important to understand the concept behind our Verilog coding. That's why I'm taking this. Input is 0 and 1. Okay. Now, so what is our next state? If we are in S naught and if my input is equal to 0, S naught input is equal to 0, we are going to S1 state, and we are going to stay in the same state. S1 input is equal to 0. S1 input is equal to 0, same state, or else next state. And S2 input is equal to 0. S2 input is equal to 0, S1 state, or else I'm going to stay in the, sorry, I'm going, so this is 0, 1, and this is 0, 0. Okay. And this is don't cares, because this particular states you don't have, right? So there will be no next state, invalid states. And here your output is 0, 0, 0, 0. And if you get here, your output will become 0 only, and here your output will become 1, right? And here also your output is don't care only. And what is your D1? D1 is just copy of Q1 plus 0, 0, 0, 0, 0, 0, 0. Sorry, here I'm going to get X, X, 0, 1. Yeah. So D1 is always 0. Am I drawing it correct? Am I doing any mistake? Please let me know. D1, let me check out. I think somewhere I've made a mistake. If I'm in S0, I'm going to S1, 0, 0. If I'm in S1, and if, okay, here I've made a mistake now. If I'm in S1, And if my input is equal to, if I'm in S1 and my input is equal to 1, I'm going to S2. S2 is nothing but 1 0. This is 1 0. Okay. And yeah. So here your D1 will be equal to 1. Okay. Yeah. And where else I'm making any mistake? Let me check it out. Anywhere do I have any other mistakes? 0 1 1 1 0 and yeah, that's it. And this is XX. Now over here, I'm just going to copy them 1 0 0 0 1 0 and X and X. That's it. So this is how I'm going to fill my transition table, right? This is not needed for writing a Verilog code. Yes, obviously it's not needed for writing a Verilog code. But if we need to understand this logic, why present state logic is a sequential logic, why next state logic is a combinational logic, and why output is a sequential or combinational logic, for understanding them, we need to have a uh, circuit diagram for that, logic diagram. So logic diagram we are going to get from this process only. Is it clear, GPT? S1 is 0, right? Yeah. 0 1 only, right? Yeah. Okay. Is it fine now? Yeah. So if we take them in terms of my D1 and I need to take the equation in terms of my Q1, Q naught and X. Okay. This is X is nothing but, sorry, M is nothing but my input over here. The minterms for my D1 is 0, 1, 2, 3, and 3 is only the minterm which I'm going to get, plus don't cares of 6 and 7 I'm going to get. And D naught I'm going to get Q1, Q naught and M, which is minterms are 0, 2, 4, 0, 2, 4, plus don't care sir, 6 and 7. And output equation with respect to Q1, Q naught, M. What we are going to get is output is only 1 whenever 0, 1, 2, 3, 4, 5, right? And plus don't care of 6 and 7. So I have already drawn my circuit in my notes. So I'm going to draw the circuit. I'm not going to waste more time over here. So let me draw that particular circuit, and I wanted to come to the main point over here. So if you solve that equations by using the K-map, you're going to get this type of circuit. So for your present states, obviously you need your flip-flops, okay? D naught and D1. And this is a synchronous circuit, right? So I'm going to have clock over here. So the same clock is going to be connected to this, right? And if I solve this, the equation for my D naught will be simply X bar. So D naught will be connected or M bar. Okay. So my D naught will be M bar, and D1, if I'm going to solve, it will be Q naught. Let me write down over here. D naught is X M bar, and D1 over here is I'm going to get Q naught bar. Sorry, only Q naught into M. This is what I'm going to get if I'm going to solve them. So I'm going to connect this via an AND gate, and I'm going to give it. Okay. And coming to my output, if I'm going to solve the equation of my output, I'm going to get Q1 into M. So this is Q1 and into M. So this is a sequence detector circuit which I'm going to get. This is my output Y. Okay, guys. So you can solve them if you find some time, then please solve it. Okay. Yeah. Now, coming to the Verilog coding part, which we have discussed previously. So what I've told that I need present state logic, next state logic, and output logic. Now tell me, for getting your present state logic, what type of circuit you are going to use. Now, what do you mean by present state? I hope now you have got clarity. Now, for getting my present state, whether I'm going to use my sequential logic or whether I'm going to use combinational logic. Present state is the output of this flip-flops. Present state is nothing but the output of the flip-flops. So I'm going to use sequential logic or combinational logic. Sequential logic only. Okay. So present state is nothing but present output of your flip-flop. What is your present output of flip-flop? Where you are going to determine your present output of your flip-flop from the output of from Q0 and Q1, right? So it's nothing but a sequential logic. Okay. Now, if you carefully observe, let's say, okay, let me draw a simple clock for you. This is my simple clock. Okay. And let's assume my Q1 and Q0 values are equal to 0, 0. So Q1 is equal to 0 and Q0 is also equal to 0. Okay. Over here, Q1 is equal to 0 and Q0 is equal to 0. Now let's say at this first passage of clock, let's say M is also equal to 0. My input is also equal to 0. Now, now tell me what will be my next state at this particular clock edge, what will be my Q0 and what will be my Q1. How I am determining the values of next values of my Q0 and Q1, which logic I am using, sequential logic or combinational logic for determining my next values of my Q0 and Q1. You can see over here, there is a combinational logic now. Depending upon your input only, your next output of flip-flop is decided. So this input must travel through this combinational logic, then only you're going to determine your next state. Am I right? So the output of this Q0 should travel through this combinational logic only, so that you're going to get the next state of this flip-flop. So next state is determined by combinational logic. Am I right or wrong? Yes or no? Is it clear, guys? That's the reason next state is basically combinational in nature. So if you want to get the next output of your flip-flops, if you want to get the next output of your flip-flops, definitely you need to compute this combinational logic. Your input must travel through this combinational logic and then it will reach to your flip-flop and then only you're going to get your next output of the flip-flop now. Okay. So that's the reason your next state logic is nothing but your combinational logic. And output, is it combinational or sequential? Can anyone tell me? Output, is it combinational or sequential? Yes, combinational only. So output is also combinational in nature. And here you can see, since it's a Mealy FSM, there is a direct connection between your input and output. And your present state is also have some role in that for determining your output. Okay. But if you feel that you need to make your output to be synchronous in nature, synchronous to clock, then you're going to add one more D flip flop over here and you're going to connect the clock so that your output will be synchronous. And from here, you're going to get your output. Is it clear? So how your Mealy, yeah, yes, people. Sorry, I didn't get your question. No, no, I haven't given any statement that output needs sequential circuits. If you want to your output to be synchronous in nature, you can give your output, you can connect a D flip-flop. Okay. Yeah. And one more point, one more important point over here. So in real time, are we going to connect these outputs directly or do we have any other extra circuit for getting our output from Q0 and Q1? Are we going to connect them directly or do we have anything uh, any type of circuit. Okay, generally in your CMOS, have you seen your output is connected via some capacitor, and from the capacitor you're going to get your outputs? Yes or no? Am I right or wrong? Yes. Yeah, I'm coming to your question, Gayatri. 1 minute. So I'm going to use some type of capacitor circuits over here. And across this capacitor, I'm going to read the outputs. Okay. Now, let's say initially the output will be equal to 0, 0. Next, what is going to happen? The output is going to change, right? It is going to change 0, 1. And next, we are going to change 1, 0. Here you can see initially the charge will be 0, 0. Next, the capacitor here Q1 is getting charged, right? Next, both the capacitors here, this will be discharging because you are going to get 0, and here it is going to charge because you are going to give high voltage, right? Now you can see the capacitor is charging and discharging for this many times. If you are going to use binary encoding, am I right or wrong? Yes or no? If you are going to use binary encoding, initially both will be equal to 0, 0. And if you are going to give 0, 1, then this means you're giving high voltage over here. And next, what you're going, since it is 0, that means you're going to discharge this capacitor and you're going to again charge this capacitor because it is getting from 0 to 1. So that means you're going to charge these capacitors and discharge these capacitors for this many times. Am I right or wrong? Since here I have only three states, so it's not a problem. But if you have more than three states, then obviously it will be a problem, right? So due to this particular behavior of charging and discharging and your binary format, the bits are going to change for every sequence. Like let's say suppose if you're going to have three bits, then 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. If you have eight number of states, then see how many times the bits are getting transition. That means how many times each capacitor from each circuit is getting charged and discharged. Am I right or wrong? Yes or no? So this will obviously consume more power. Am I right or wrong? Yeah. So that's the reason if our concern is to use, if our concern is to have less power consumption, then we are going to another type of encoding, which is known as gray encoding. So in the gray code, you can see each digit bit change for every sequence, for every adjacent sequence, your bit change will be only one. Here, only one bit change, and here, only one bit change, and here, only one bit change. So, we are going to have the gray encoding, and where we are using this gray encoding for representing the states. Here you can see for representing this S naught, you are going to use 0, 0, 0, 1, 1, 0, 1, 1, right? So instead of this binary encoding, you are going to use gray encoding like this 0, 1, 1, 1, and 1, 0. Is it clear? That we are going to discuss next. Okay. Not today. We are going to have the discussion. I think mostly tomorrow. Okay. Yes. So that is what the fundamentals I wanted to introduce about this. And in next session, what we will do is we will discuss some problems related to FSM, like what are the possible related problems related to FSM. Next, we are going to discuss some of the coding techniques in Verilog related to FSM and some of the debugging things we need in FSM. Okay. Yeah, application based. And debugging matlab like let's say suppose if we are going to use okay, by mistakenly if we have used a counter logic in a combinational logic. Okay. So whether you can say your counter is going to work. Let's say you have written a counter logic, but in a combinational block, but not in a sequential block. Your FSM is going to have two blocks, right? Sequential and combinational. Now tell me whether your counter is going to work or not. Others also you can answer. And 1 minute, I will bring my charger. State logic. So the counter logic I'm going to write down in next state logic. So what do you think? Is it going to work? Okay. Okay. What about others? Okay. So basically, it is not going to work because the next state logic is a combinational logic. The next state logic is a combinational logic. So your counter is not going to increment as you have expected. So the question is simple. Let me show you the question again. So my question is, so Verilog coding has three blocks, right? Present state logic, next state logic, output logic. So the counter incrementing, let's say some requirement we have, and we have written the counter incremental logic in the next state. This block we have written. Is it going to work or not? Is my question. Did you get it now, ChatGPT? Okay, no issue. I will show you in the coding part. It will be more clear. Okay, so that is a bug. So that bug, generally what happens is we normally use them, but we overcare it. Like we don't we overlook it. Like we will not be overseeing it. So that's the reason it's a bug. So I will show you that kind of bugs in FSM. Okay. Yes, Gayatri. So what is your question? Melee is asynchronous, but you use it clock synchronously. Yeah, so you can also make your output to be synchronous in nature. That means if you're going to add one more output here, if you're going to add one more flip flop, there is no issue in that. To make your output synchronous, you can add flip flop. Okay, Gayatri. For yeah, you can watch the. Okay, I will share that playlist.